Okay, so welcome to Math389. I'm teaching 3 classes back to back to back in this room, so if I'm ever giving the wrong lecture, just let me know, and hopefully I can adjust. Is there anybody taking more than 1 class with me this semester? All right, so you might actually hear the same material multiple times during the day because it's kind of hard to prepare 3 different lectures. So give me a little bit of leeway first before you say it's the wrong lecture. All right, so just a couple of things first. I like to have a vote on cell phone policy. Option A, if someone's cell phone goes off once, the class gets a warning, and then the second time everybody gets a quiz. Option B, whoever's cell phone goes off has to provide munchkins and or healthy snacks for the next class. How many want option A? How many want option B? Option B passes, okay? So if your cell phone goes off, you are now responsible for bringing Dunkin' Donuts munchkins or something equivalent to be approved by the class, and something healthy because I'm trying to keep the weight off, okay? My cell phone is 617-835-3982. You are welcome to try to call me during class, or have some of your friends try to call me during class to make sure my cell phone is off, as it should be, yes, okay? If you are expecting an extremely important call, by all means, do not put your phone on vibrate, just let me know. All right, so I thought I would go through a little bit of the basics. This is essentially a graduate level class. The only thing that's different between, well, okay, I guess 2 things that are different. First, it says Williams College and not Williams University. And the other difference is it's, oh, it doesn't say it here. I would say 9 a.m. Normally in grad school, you would not be taking a class at 9 a.m. That's one of the advantages of making it to graduate school, okay? There's got to be something that balances out everything else that's happening, okay? This is one of the few things. All right. So this should be advanced analysis. The actual content of this class is going to depend a little bit about you. Essentially, I want you to get a sense of what is graduate school like? Is it for you? In particular, what is math grad school like? And what can we do to get you into the best grad school possible? And I'll go into a little bit more detail about this in a moment. All right, so for me, I actually get to look at the lecture through the camera, but it's all reflected and inverted. So it's a little hard, so I will sometimes turn back. So obviously, I want you to learn. Sorry, question or? Oh, yes. Didn't even make it 5 minutes. It gets easier, don't worry, it gets easier. All right, so the first is obviously I want you to learn advanced analysis. Williams requires me to submit some kind of syllabus and some kind of course description, so I have to be a little bit general because I want to maintain flexibility of adjusting the material. I really do not have too much of an agenda other than we will cover the circle method. When I was a postdoc at Ohio State years ago, I was asked, what do I think the most beautiful idea in mathematics is? And I said the circle method. And one of the professors kind of laughed at me and said, you're young. All right, it's been many years. I still think the circle method is the most beautiful idea I've seen in mathematics. It allows you to handle problems such as, can you write every large even number as the sum of 2 primes? And conjecturally, what does large mean? No. I want to write every large even number as the sum of 2 primes. Conjecturally, what do we believe large is?
More than greater than 4.
No.
Greater than or equal to 4?
Greater than or equal to 4, yes. More than 4 is, no, that's excessive. Now, if you want to just use odd primes and discriminate, that's acceptable in this department. Right? There's certain types of discrimination. And in fact, we will see that we will discriminate amongst primes, and we will not count all primes equally. We will introduce logarithmic weights that are slowly varying. As long as you control how much you discriminate, you can get away with it. And in fact, it makes a lot of the calculations easier. We'll see stuff on the Riemann zeta function. We're going to do some stuff on Benford's law. One of the reasons is we're going to lead from Benford's law into Fourier analysis and then back into Benford's law. Fourier analysis occurs in a lot of different fields. Out of curiosity, how many of you have gone deeply in Fourier analysis? Because we've got a couple of people. So you've seen convergence theorems, pointwise convergence theorems. All right, so I apologize if you're a little bit bored for that part, but I will make it up to you later in the semester. All right, so we will see topics like that, but if there are other things that you want to see, this is your chance to have some control over what we do in the class. There are so many different topics. This is one of the reasons I like the book. The other is, of course, I get the royalties. I unfortunately chose Princeton University Press because they keep the price of the book down relative to other places. The book price may be cropping up a little bit. Unless you're writing a calculus book, you don't write math books to make money. That said, you can get other things for writing math books, and so we will all be writing a math book this semester. Okay? So I am the problem editor for Mu Epsilon, the Undergraduate Math Honor Society. And so one of the things that I did at the start of my tenure is this is the 100th anniversary of the Math Society. And I thought it would be really fun to celebrate with a list. Everybody likes to do lists. And what I thought to do is, let's do one problem related to some mathematical event from each of the last 100 years. So a good chunk of these are already done. I already have over 80% done. I had basically 2 or 3 months lead time from when the project started to when the first issue had to come out. So I decided, let's publish things in groups of modulo 4. So modulo 0 mod 4 and 1 mod 4, 1 mod 4, 2 mod 4 have been done. 3 mod 4 is almost done. 4 mod 4 needs a little bit more work. So there are 2 ways for you to get involved in stuff like this. One is to actually write some of the problems for some of these years. And in the Mu Epsilon journal, these are going to be short descriptions. I've also talked with the MAA, and I have an agreement in principle to turn this into a book. And so to turn it into the book, we want to take these write-ups for the years and expand them. So there's a small number of you, there's a large number of problems, you can do the division. And what I would like to do is I would like your help in converting these to little small sections for books, as well as writing some of the years that I'm missing. This is a great way to see some of the most important mathematics. Some of the events that are chosen may not be as important as others. Why? Well, sometimes deadlines were coming up and people who promised me they were going to contribute did not, had to quickly do things at the last minute. Other things is what's going to be appealing to an undergraduate audience. Part of it is I want people to get a sense of what's out there in mathematics, but I want it to be accessible. And so sometimes I went for more recreational math, some more fun math, or just some things on math history. And so there's a lot of good stuff along these lines. You'll see a lot of good mathematics. All right, so in addition to stuff like that, everyone is going to review from Math389. So I was talking with Professor Garrity yesterday, and one of the things he remarked upon is that mathematics is often far ahead of other disciplines in terms of embracing where things are going. And so going all the way back to the 1930s, we already had an indexing service where people reviewed math articles and posted these reviews. Now, of course, it was not online back then. You had these bound volumes. But there were wonderful descriptions about what the articles were about. These are not editorial descriptions about what an article is like, as much as you want to avoid it. One of my students this summer showed me a website of people who have taken the Math389 reviews that were editorial and have collected them. And there's a couple of truly atrocious papers that were published. And people have responded in the only way appropriate by actually blasting them in the reviews. So there's some really good reviews of bad papers on Fermat's last theorem and other things. I'll try to share those links. It's really worth reading. I have gotten 2 journals banned from Math389. I'm very proud about this. A couple of years ago, I'm very proud. There's several people who did small with me this past summer. You have not seen me explode. A couple of summers ago, I got a paper to review. It was published in something like the Interdisciplinary Journal of Mathematics or the Journal of Interdisciplinary Mathematics. It's like the Life of Brian. I forget which way they ordered them. But it claimed to prove the Riemann hypothesis, and it claimed to disprove the Birch-Swinnerton-Dyer problem. These are 2 of the 7 Clay problems. One of the Clay problems has been proven. If you haven't heard of the Clay problems, these are supposed to be the problems that will influence the development of mathematics in this century. It's in some sense a sequel to Hilbert's problems from the turn of the century before. Except we only have 6 or 7. Each one of them comes with $1 million prize. There are requirements as to what must happen to collect the $1 million prize. So far, one of them, the Poincare conjecture, has been solved, but Perelman, who solved it, has declined the $1 million. He's also declined the Fields Medal. It's an interesting story. Yes?
Did you do that because you wanted to avoid attention to himself?
No, because if you're trying to avoid attention, this gives you even more attention. And in fact, he's now the most famous non-Fields medalist of all time.
Okay.
And so, it's interesting. I mean, you could take the $1 million and you could have a bonfire. You could basically just have a plane flying and drop them. There's lots of fun things you could do. But he's made a statement about what he thinks about math prizes. And if you read what he's saying, there is some merit to what he believes. And in fact, some of my students know here, got to be a little careful because this is being recorded. In previous years, the Young Mathematicians Conference has had cash prizes for talks. And I'm very glad that after years of agitating, they finally went to no cash prizes this year. But the paper was resolving 2 of the 6 open Clay problems. How many of you have seen the Riemann zeta function? Okay. It's normally defined as the sum of 1 over n to the s, or the sum of n to the negative s, where n ranges over the integers. The person who proved this, I'll wait till you stop drinking. The person who proved this wrote it as the sum of n to the tilde s. So if you've heard the story, you cannot answer. Any ideas why he said tilde s? He's a logician. And so the way he wrote negative s was not s. This gives you an idea of the academic merit of this paper. Now, I was honest. I read the paper carefully before I wrote my review for Math389, and I told them, if you absolutely must publish a review of this paper, here is one, but I would much rather prefer that you just ban the journal. Because anything that would let this get through the refereeing process is not serious. And so Math389, I've worked for them. My students have worked for them for many years. They wrote back to me and they said, all right, we will take your comments under advisement and we will get back to you. By that afternoon, the journal was banned. No, and I mean, this is truly atrocious. It should not be something like this. I will not have you reviewing papers like that, okay, hopefully. Some of my students this summer actually discovered a paper. They were trying to decide if it was worth publishing. I think in the end we decided it was not worth publishing, even though someone else had already published the exact same paper word for word. Most of the time this will not happen. I will have you working with reputable journals, I'm going to be careful. I will have you working with reputable journals. I've got to get used to the habit of this is being recorded and have to be careful what I say. It is a very good idea to referee for journals. Why do you do this? 1, you get experience. 2, you make friends. 3, you get to see what's out there mathematically. So there's a lot of good things. How many of you are thinking of applying for an NSF graduate fellowship either now or in the future? If you do not have your hand up, you should not be considering graduate school. Right? You want to apply for these fellowships. If you get in, it's almost a go to university free card. Because you can call up the school and say, I just wanted to check on the status of my application. I and my NSF graduate fellowship are very interested in coming to your institution. And you could often get back and says, really, this is a coincidence. We were just about to contact you and your NSF fellowship to let you know that you are off the wait list. And so it can make a huge difference. The other thing is the more people who apply in math, the more math graduate fellowships go out. So even if you don't have a chance, you don't think you have a chance, you can still help your friends who are smarter than you. Okay? Nice, compassionate thing to say. Okay? But if you want to do stuff like this, one of the things they ask for is broader impact activities. And you have to decide, well, what does that mean? Different people will construe broader impact in different ways. One is going and talking to younger people and getting them excited about mathematics. Another is doing service to the mathematics community. A senior colleague of mine a couple of years ago had a paper under review at a journal. I'm not allowed to say the name of the person or the journal, but I will say that after the paper had been languishing for 1 year without any news, he contacted the editor and said, I am withdrawing the paper. Please inform the reviewers, if any. And sadly, this is not uncommon in mathematics. People often do not do a good job reviewing. There's a lot of reasons. We get essentially no credit for it. We don't get paid for it. It can be a lot of hard work. But my feeling is if you agree to do something, you should do it, and you should do it in a reasonable manner. So get things out of your inbox as fast as possible. It is a great way to impress people. And so, you know, if you're going to do a review for a paper, journals will be very appreciative. And this really is a service to the mathematics community because there is a huge bottleneck of papers that are waiting for referees. So if you guys can referee some papers, this is another thing you can write about for broader impact as well as the Math389. Okay, another thing is to find out if grad school is what you want. So later today, I'm going to hit you with what happened to me when I was becoming a Peter Sanek student. So I was very fortunate. I had 2 thesis advisors, Peter Sanek at Princeton and Henrik Ivanitz at Rutgers. And I still remember the day my colleague Eduardo Duenas and I went to Sanek's office to officially become Sanek students. And so he had already had us in class. He knew us a bit. We were talking to him and he said, okay, well, let's see. You should probably read the following paper. That would be really good. And if you're going to read this, you probably actually need to read this as well to make sense of that. And then this would actually be useful as well for that. And then the pile of papers he gave us kept growing. And I believe the only reason it was capped at a finite number is the phone rang and it was his youngest daughter who needed to be picked up from soccer practice. And if there hadn't been a phone call, I think we would have just had more and more papers to read. This is how grad school is. And you know, again, I am teaching a 3-1 this semester. This is not my choice. This is to help out the department and the college. When you're at a liberal arts institution, as you know, we do not have large numbers of staff. We cannot afford to offer multiple sections at the same time, or I guess not at the same time, slightly different times, same semester. And you have to figure out, well, when can I take this class? When should I do things? And there are certain needs that the department and the college had. This class cannot be offered in the spring, or it's not going to help anybody who's applying to grad school this year. The point is for me to be able to write really good letters of recommendation for you now. For the people who aren't seniors, that's fine. But for the people who are close to graduating, this class has to be offered now. I'm teaching a class on problem solving in the Putnam. Okay, if you offer that in the spring, it's really pointless. I guess it's really anticipatory for the following year, but you don't really want to train that far in advance. So those 2 classes were fixed. And then I'm also offering operations research. The college department needed a pre-core 300, which has over 40 students right now. So I'm extremely busy right now. If I'm in my office, it's office hours. Several of you have met me before, and if you send me an email late at night, you will get a response within 3 hours. I may have to slip to 4 hours this year for health reasons. I'm not sure yet. I will try. But I am going to be extremely busy. But this is a good thing for you. Again, you should definitely try to talk to me. You should definitely come to my office. I will definitely keep myself accessible. But who is your first line of defense? I know this is being recorded. Who's the first ones you should go to? Classmates, each other. You're all in this together, right? This is what grad school is like. When you're trying to decide where to go to, one huge factor is who is going to be your thesis advisor, or who is going to be related to your thesis advisor, who's going to be working in that field. A lot of people like to go to big schools because there's a lot of people working in certain areas. You can meet the professors, the postdocs. There'll be lots of activity going on. Williams is not what graduate school is like. If you are thinking of working in the outskirts of your advisor's office and camping out and then going to them when you have a question and getting an immediate response, think again. The amount of accessibility greatly goes down in most graduate programs. Now, there are some graduate programs that are extremely friendly, that work very hard to keep the professors accessible. This is not to say that your professors will not see you. I remember times when I would spend over an hour waiting outside for an appointment I had with a professor because they were busy with other things. If it was a real emergency, I remember the day my thesis collapsed and I realized, oh, I had dropped this condition. My advisor quickly cleared up his calendar and made time to see me that very day. But otherwise, okay, I just have some grading to do, I have some work to do. I can do it outside their office, I can do it in the library just as well. People are busy. Postdocs often have more free time. And for me, I found postdocs were a lot easier to talk to. And so one nice thing about going to a large school is you have a lot of postdocs to talk to. But that said, there are far more graduate students. You want to go to a place where there's a bunch of people studying the same thing as you. And the advantage of something like that is you will have people to talk to who are in the same boat. And then, I don't understand this, you don't understand this, maybe we can figure it out together. And if you figure it out together, you often learn it a lot better than if you have someone give you the idea of how to do it. When I was in graduate school, my advisor would often ask me, do you know X? And I would quickly make the following calculation. Can I learn X by the next meeting and kind of fake my way through it today? Yes, I know X. And if I felt the answer was no, I would say, no, I do not know X, and I would just be upfront and admit it. And there were some things I knew. I can quickly learn what that is, and there were other things that I have absolutely no idea. Could you give me a quick explanation? My advisor does not have time to give me tutorials on everything. And so I am going to hit you with exactly the same thing on the first day of class. We're going to talk a little bit about some things, and then if you don't know some things, you are responsible for learning it by Monday. Or, instead of learning it, what? Being able to fake it. Right? Yes? So you have to either learn the material or be able to fake it well enough to fool me on Monday. And then quickly learn it in the next few days. There will be at least several people in this class who will be able to help with stuff like this. I am not sure what is the best way to do something like this. We might want to have a discussion group where people can chime in. If somebody wants to take point in organizing something like this part I don't mind being recorded. I do not use Glow. I'm happy to set up something on Glow if you want. But OIT and all the different colleges and universities I've been at, they keep changing their system for courses. I keep doing my primitive HTML code. The web pages do not look that pretty, but they're functional and the information is there. But if you guys want to have a discussion board to facilitate stuff like this, I'm stuck on the following. Can anybody help with something like this? By all means, I'm happy to do something like that. And just if somebody wants to take point on that, let me know. Okay, so hopefully this gives you, some rough idea of the goals for the course. I've got to be careful and learn how to go like this so it doesn't change how the camera is going. All right, so over here's a couple of problems that we will be looking at. The first is Benford's law. So we have 2 experts in the class and 1 expert who is taking the class remotely due to scheduling conflicts on Benford's law. So Benford's law of digit bias is one of my favorite topics. And what I love about this is it cuts across many different disciplines. So I have just finished editing a book on Benford's law, and your homework for Monday is to read chapter 1 of that book. Chapter 1 is pretty friendly, not too much mathematics, just a broad overview. There is some basic probability you need to know. If you do not know basic probability, read chapter 8 of the textbook for this class. And I think in the notes I tell you exactly how far in chapter 8 you have to be comfortable with. If you know mean, variance, standard deviation, well, if you know variance, you should know standard deviation, a few basic distributions, that should be enough probability. If not, there's at least 4 or 5 people in this class who know enough probability who can help with something like that. So Benford's law is one of the types of problems I want to do. The next is the circle method, and I've talked a little bit about that. It turns out you can convert a lot of very difficult problems, such as can any large even number be written as the sum of 2 primes, to an integral. Is this a good thing or a bad thing? Seems like a good thing. The difficulty, of course, is that most of these integrals cannot be done. So when you take calculus, the big lie, at least in Calc 1 and Calc 2, is that integration is easy. It's easier than other things, yes. It's much easier than doing sums. But in general, you cannot get closed form expressions. So what the circle method is you convert what you want to solve, counting how many solutions there are to something, counting as to whether or not something happens, to an integral, and then trying to estimate the size of the integral. And if you can show the integral is positive, you show something happens. The proof technique is one of my favorites. So if you want to show every large even number is the sum of 2 primes, one way to do this is show that every large even number can be written as the sum of 2 primes at least once. And if you can do it at least once, you're done. Well, doing it at least once is actually very hard. What you do is you show every large even number can be written as the sum of 2 primes in many ways. And if it can be written as the sum of 2 primes in many ways, it can be written as the sum of 2 primes at least once. So you get a really good estimate for the number of ways something happens. And if it happens many times, it must happen at least once. How many of you have seen Dirichlet's theorems for primes and arithmetic progressions? So there's infinitely many primes. There's probably infinitely many proof that there are infinitely many primes. You can look at primes in arithmetic progressions. So primes that have the same congruence modulo a number. So primes that are congruent to 3 mod 5. They always have remainder 3 when you divide by 5. And it turns out, as long as you don't do anything stupid, there are infinitely many primes congruent to A mod B. What is the one stupid thing you must avoid? So I want to prove that there are infinitely many primes congruent to A mod B. I have to be careful about one stupid condition.
Setting A equal to 0.
Okay, A equals 0. Yes, well, a little bit less stupid than that. Yes. Okay, A and B both even a little bit less stupid than that. You're being excessively stupid. You can still just be a little, yes.
A and B relatively prime.
A and B are relatively prime. If A and B have a common fact, if A and B are both divisible by 17, then you are not going to find infinitely many primes congruent to A mod B. You'll have at most a finite number. I'll let you think exactly how many that finite number would be. It's not that hard of a calculation. So as long as you avoid something like that, you can prove that there are infinitely many primes congruent to A mod B. The interesting thing is the only way we know how to prove that there's at least one prime congruent to A mod B in general is to prove that there are infinitely many primes, and therefore there must be one prime. It's ridiculous. We can't prove that there's just one in an easy way in general. In some special cases for A's and B's, we can. One of the big things that I want to try to emphasize in this course is how to think about mathematics. Mathematics is not meant to be passive. Mathematics is meant to be active. So I have deliberately not prepared too much for my classes this semester. Okay? This is, again, I've got a 3-1, but also I want to have a lot of discussion from you and I want you to have some control. Most of mathematics is trained monkey work, using the techniques that everybody else has and adding your little piece. And that's good, that's important. but the real action is coming up with good questions. So we've already talked about there are infinitely many primes congruent to A mod B if A and B are relatively prime. What are some questions I could ask about these primes? So give me some questions. What would you like to know?
How large does the spacing get between them?
How large does the spacing get between them? And so it turns out you could talk about the average spacing, and you can talk about how large is the spacing between them relative to the average spacing between them. In the case of just the primes, that was only essentially recently proved in the past month, where finally two different teams resolved a conjecture of Odish about how large spacings between adjacent primes can be relative to the average spacing. So this was a very deep, very difficult question. So that's a great thing to ask. I don't know if their techniques have been applied to arithmetic progressions. I would assume that it would follow through without too much trouble. Great question. What else could we ask? So we're looking at primes congruent to A mod B. We know there's infinitely many. What else could we ask? So you've got a bunch of objects. What do you want to know about the objects? Any Chicago Cubs fans here? Any baseball fans here? All right, what do you think a Chicago Cub fan would love to know?
When they'll next win the World Series?
When they'll next win the World Series. So this is related to the question about gaps. We could ask, when do we find the first prime congruent to A mod B? How long do we have to wait? Well, if A is prime, it's not that difficult of a question. But if A is composite, it becomes a very hard question. And we actually have some upper bounds as to how long you have to wait. If you wait this long, you will see. So when I was young, I asked my great uncle, who was a huge Red Sox fan, I think I was about somewhere between 3 and 7, will I live long enough to see the Red Sox win the World Series? And he assured me I would. I should have asked him what else I would see based on what's happening this year. But this is one of the biggest questions you want to know in mathematics. How long do I have to wait until something interesting happens? Another one is, how many objects are there? And again, a lot of these questions are related. If I count up to x, how many primes are there that are congruent to A mod B? Another one is to look at several of these progressions at the same time. So let's look at the primes congruent to 1 mod 5, 2 mod 5, 3 mod 5, 4 mod 5. All right, I won't do 5 mod 5. All right, let's look at these progressions. What might you want to ask about them? So we've got 4 different progressions. What might I want to ask? Yes?
Is it about the same number in each one?
Is it about the same number? And to first order, yes. To first order, they all have the same number. So after you prove that, which is what Dirichlet did, you celebrate, you jump for joy, and then you subtract off the main term. And now what do you ask?
Same question.
Okay, well, now rephrase.
Are the lower order terms the same?
Are the lower order terms the same? And this leads to a wonderful subject called Chebyshev's bias, where it was observed that certain residue classes seem to have more primes most of the time. They seem to be winning. And this is related to Skew's number, which for a while was the largest finite number in mathematics. And it turns out that they flip infinitely often between these residue classes. On a logarithmic scale, each one wins a positive percent of the time, but some of them win like 99.999% on a logarithmic scale. So there are some residue classes that have a huge disadvantage. A lot of it comes down to whether or not your number is a quadratic residue or non-residue modulo the modulus. And if you don't know what that means, it's not too important right now. But we also have 4 different residue classes. I could ask, there are 4 factorial or 24 different ways to order the 4 factorial, the 4 residue classes. Is it possible to find an x such that whatever ordering I want happens? Given an ordering, can I find infinitely many x such that this happens? Does this happen a positive percent of the time? Does it happen a positive percent of the time on a logarithmic scale? What is true about which ones are winning, which ones are not winning? What happens as the modulus gets large? Does the bias between the residue classes get larger or smaller as the bias grows? So there's lots of great questions you can ask. A lot of this was done in a paper by my advisor, Peter Sarnak, and his undergraduate thesis student, Michael Rubenstein, who then became a graduate student of Sarnak at Princeton. This was his undergraduate thesis. Beautiful paper, Chebyshev's bias. And the story I've heard is it essentially knocked out computation at Princeton Math for a couple of days. Email was essentially slowed down to nothing. This was, early 90s. It wasn't a big deal back then. But, wonderful interplay between computational mathematics and pure number theory. Now, to make progress in a lot of these questions, you often have to assume big hypotheses. And so here, if you've heard of the Riemann hypothesis, that's not enough. If you've heard of the generalized Riemann hypothesis, that's not enough. We have to go one step further to the grand simplicity hypothesis, which says, and it's okay if these terms don't make full sense, the zeros of L functions on the critical line are linearly independent over the rationals because why not? It's just too strange to imagine that there could be some kind of linear relation involving rational multiples of them summing to 0. And what this eventually gives you is it gives you a flow on a certain torus. It is ergodic, it fills up the space, and you see wonderful connections between number theory and ergodic theory. There's a lot of connections right now between number theory and ergodic theory. You'll be seeing a connection later on. Ohio State, where I was a postdoc for a year, has wonderful Professor Vitaly Bergelson, who's had a lot of students and postdocs and colleagues working on problems like this. You might have heard of like Terence Tao and Ben Green's result a couple of years ago that the primes contain arbitrarily long arithmetic progressions. And so there's a lot of great stuff to look at in things like this. So I've been talking a little bit about L functions right now. I'm getting better at reading things in reverse and flipped. And the last one looks like Poissonian behavior, which is going to be related to Benford's law. It's related to spacings between things. If I have to summarize my research in one sentence, I would basically say I study how long it is until something interesting happens. And depending on whom I'm talking to, I define something interesting in a different way. It could be how long until I get the next prime, the next zero of the Riemann zeta function, the next energy level of heavy nucleus, the next summit in the Zeckendorf decomposition, the next World Series victory of the Red Sox. What one of my former students have noted is that either the Red Sox or the San Francisco Giants win the World Series in years when they play each other in the regular season. So the next chance the Sox have is, I think, 2016. Okay. So over here, course mechanics. So the first over here is a rough description of how the course grading scheme is going. Because this is being recorded, I will just say that this is rough. I am happy to have this adjusted a little bit. I want you guys viewing yourselves as graduate students, not as undergraduates. What this means is cookbook exam problems, cookbook homework problems, this is not what life is about. When I was a student, I wanted to prove theorems in the greatest possible generality because I wasn't really doing anything with them. When I got to grad school and I actually found problems I cared about, oh, my function is infinitely differentiable. I don't have to worry about my function is only continuous. And so I don't mind putting in a lot of extra conditions to have the proof simplified because in a lot of the applications, these conditions are met. Now, not always, but it's not a bad assumption to start with. I want to get you guys doing some research projects if possible. One thing is if you're interested, there's a research project in Benford's law which has applications to economics and finance, which I'm happy to talk a little bit more about. I have some stuff in Zeckendorf decompositions. I have a project for a student if you want to do something like that. Bless you, I'm happy to talk more about stuff like this. A couple of papers in elementary number theory. I want you guys doing research. I don't really care if you get results. It would be nice. The main thing is for you to get a sense of what is research like. Is this something you want to do? What are the techniques? How do you take a complicated article and read it? How do you distill the key idea? This shirt is designed to distill the key idea of the proof of Fermat's last theorem. This is still incomprehensible to me, but, mostly incomprehensible. Well, I guess there's a few stuff towards the bottom that are getting a little bit hard. But it's enough to give a flavor of what's going on. And when you're doing research, this is a really difficult thing. How much time do you spend learning every single result and making sure everything is correct? If you spend too much time, you don't have time to prove anything new. But if you don't, there's always a danger. There was a thesis defense at Princeton many years ago. I forget if it was Mather or Milner in the audience. They're listening to the defense and they go, your result is very interesting, but what about the following? It satisfies all of your conditions and all your hypotheses, but not your conclusion. And so the graduate student is trying to explain why it's not a contradiction, and the thesis advisor is just trying to see how well his student can do. And when it's clear that his student is floundering, the thesis advisor comes in to save the day, but can't. And a counterexample to the guy's thesis was discovered on the spot. So you're Princeton University. The student made a good faith effort to prove a dissertation. The advisor thought it was correct. It's not. What do? Thesis or no thesis? No thesis, exactly. That's why you can trust me, because I have been vetted by a very good institution that has standards. Now, of course, Princeton has a heart, right? They let the guy stay for an extra year. It turns out he was using a result that was published in the top journal of mathematics that was wrong. And so he had to correct that paper and then put in some additional conditions and then further restrict the class of examples his work applied to. And in the end, this was very good for him. It was good that this happened when he was a graduate student. He could take another year, fix things, fix the paper, get some publications, then have this happen later in his career. But you've got to be very careful. You know, refereeing is sadly not always well done. All right, so other stuff is prerequisites, real analysis. That should not be a surprise. Abstract algebra would be nice, but since I have never taken abstract algebra, I don't feel comfortable having that as a prerequisite. I don't want to have you guys doing things that I would not have myself do. I have at least taken Galois theory. At some point I will tell you about when Serge Lang dragged me out of class about my lack of algebra background. All right, the other thing is office hours. So whenever I'm in my office, it's office hours. Email me. I am flexible in terms of when things are. You should also be talking with each other. All right, this is a small enough class that you can get to know each other, you can get to know me, you can do these things. The other thing is issues may arise either in this class or other classes. I will not say what institution this was at, but one school, 3 of my former students came to my office one day and they said, "Can I talk to you? Can we talk to you?" I said, "Sure." And they closed the door. And I apologize for those of you who already know the story. It's never a good sign when students want to close the door in your office. And so I said, "Okay, well, what's going on?" I said, "Well, we're supposed to be taking group theory." And I'm not always the kindest person. I said, "Okay, so go to group theory." I said, "Well, we can't." "Well, why can't you?" "The professor's teaching the wrong course." "I'm sorry?" "He prepared the wrong course over the summer. He prepared Galois theory." "Well, did you tell him this?" "Uh-huh." "And what did he say?" "Well, how much group theory do you need to know for Galois theory?" "I'll teach you the group theory you need to know in a week." Okay. This was not an ideal situation. Okay? Hopefully, whenever I screw up, I am usually very good about admitting that I have screwed up. And I see people nodding their heads a little bit too quickly. But you should feel free to come and talk to me. Okay? The only way I get better is when you tell me when I do something wrong. But there are times when you may not want to talk to me, or maybe it's somebody else who has screwed up, either in our department, in the college, in the country, in the world. Depending on how far away you go from Williams, my control gets less. You know, I would love to wave a wand and stop terrorism. I don't quite have that power. I can't balance the budget. But if you have concerns, here's a way to anonymously email me. The closer it is to 389 and stuff at Williams, the more effective it will be. But the password is the first 8 Fibonacci numbers. For those of you who have worked with me this summer, we will use the standard definition of the Fibonacci numbers here for the email account. Do not change the password, okay? But this is a way for you to email me anonymously. And if you want me to respond back, just write back, either email me at this anonymous address, or just respond back to Eve's Math. And I'll just send a response back there fairly quickly, and you'll know to just log in and check. Okay, but again, if you do have any concerns or questions that you do not feel comfortable, please bring it to my attention. And this normally happens a couple of times a semester. And this is just a nice way to go about things. Okay, so over here, this says, web pages, okay. Yes, web pages, okay. So I try to have very good, extensive web pages. If there's additional things you want, if there are additional resources that would help you, let me know. I am happy to put the stuff up there. As I mentioned, we will be writing a book in this class, which I find exciting. It will be done by the end of the semester, because we have no choice. All right. The last is prepare for class. You must do the readings before class. I have 2 little kids at home. I don't think I actually have pictures that I'm going to be showing of them right now. Hey, I can probably show a picture. Hell yeah. All right, so now I have to go back so we can actually get into the video. Okay, so there is Cameron and Kayla. Okay, I have 2 kids at home. I can deal with kids at home. I can deal with little kids. I don't want to be dealing with little kids in an advanced analysis class. I don't want to be checking up and giving you little pop quizzes to make sure you've done the reading. All right. Do the reading or do enough so that you can fool me into believing that you have done the reading and can hold a conversation. Okay? It will make this class far more enjoyable and far more productive. I do not want to spend the time going through algebra and regurgitating things in the book. I trust at this point that you can read. And when I say read, I do not mean Ulysses. I don't mean Shakespeare. Okay? I mean you can read mathematics. Okay? You should be able, at this point, to be able to pick up a book and go through it and master it. In class, you should be able to get the key idea of the arguments and the main brushstrokes of the idea of the proof, and then fill in the details later. When I was a freshman, it was very jarring to switch from classes in high school where everything was done to classes where things were left to you as the homework. And for a while, I thought Rita was the greatest mathematician of the 20th century because every other page in my book was always leaving something to Rita to do. Right? This is how you learn mathematics. You learn mathematics by doing. Okay? And that's why it is left to you. Davenport's multiplicative number theory was essentially an ante to be a Peter Sinek student. This was back before the days of bootleg PDF files on the web. What we would do, we're going to be very careful. The book was out of print. And so when things are out of print, sometimes people might Xerox copies. Of course, we would never do that because that would be wrong. But you might have gotten a Xerox copy of it when you became a Sinek student. And then as soon as the book came in the 3rd edition, we all rushed and bought it. You can look at these books and just see how many notes we have in the margins of trying to fill in the gaps in these statements of the proofs. This is how you learn mathematics, is you go through it line by line by line. That's the best way to learn it. Okay. So over here now, my Odish number is 2. Is there anybody here who does not know what an Odish number is? Okay, so have you heard of the Kevin Bacon number? So it's how many movies do you have to go through before you've been in a movie with somebody who's been in a movie with somebody who's been in a movie with Kevin Bacon? And so in mathematics, Kevin Bacon hasn't really played too important of a role. Who has played a more important role in mathematics? Odish. And so in fact, if you go to Math389, they actually have a calculate my Odish number button. And you just punch this button, it will immediately tell you what your Odish number is. This is a great graph theory question because it's a huge network and trying to figure out what's the most efficient way. So my Odish number is 2. It's not clear what my Odish-Bacon number is. The Odish-Bacon number is the sum of your Odish number and your Bacon number. It would have been definitely smaller if I had been in the movie that we were making for Professor Adams's book on zombies. There was a little TV show that was being produced, but I gave the part to my students instead. It's not clear whether or not something I've done counts, so my Odish-Bacon number might be infinite. Natalie Portman actually has a really good Odish-Bacon number. And I forget her name, the girl from Wonder Years. She also has a really good Odish-Bacon number. One of my colleagues, John Conway, came up with another number, the drinking number. Have you had a drink with someone who's had a drink with someone who's had a drink with? And so this is Vitaly Bergelson from Ohio State. He is an expert in number theory, ergodic theory, very nice guy. I saw him recently at the Young Mathematicians Conference. This was the night I bailed on you guys. Because it was not clear if I had drunk with him when Furstenberg was at his house, it was extremely important that I made sure that we had shots and some stuff that night so that if you now have a drink with me, your drinking number will be very good. And drinking numbers are much easier to get and a little bit more enjoyable to get sometimes than Odish numbers. A lot less work, but sometimes harder to remember. Who was there at the time? You have all these different requirements as to what counts as a drinking number. So I was at a table with Cyr a couple of months ago. We both had wine that night in France. Does that count? I think it counts because we were at the same table. I don't think you actually have to tap glasses or whatnot. So you can have all these different tweaks on the problem. But here's an interesting question. What do you think my Gauss drinking number is? Anybody want to make a guess? And this is going to be damn hard to prove, right? But I mean, order of magnitude. Somebody give me an order of magnitude estimate for my Gauss number, Gauss drinking number.
Did Gauss even drink?
If he had students, yes. What would you think? Anybody know roughly when Gauss was active? 1800s. All right, close enough, 1800s. So how far back do you think I need to go to get a Gauss drinking number? 150 drinks or 150 years?
No, drinks.
150 drinks. Because, I mean, I'm going to be very careful because this is being recorded. Vitaly Bergelson has gone to international, the big meetings. I am sure he has drunk with a lot of key people over the years. I've drunk with Cyr, I've probably drunk with Furstenberg, if not Bergelson. He's a Furstenberg student, he's drunk with Furstenberg. So that gets me back pretty far.
you ever drunk in Germany?
Not in Germany, no. I've only been in the airports there. But what do you think? Do you think it's on the order of 5, 10, 50? What would you think?
19.
I'm sorry? I think between 5 and 10. I think by 10, that's overkill. Because, you know, again, you can get somebody at the tail end of their career who then drank at the beginning of their career. So one of my former students was on the baseball team here. He was playing golf a few years back with some people who had been on the baseball team in the 1970s. And the coach for the Williams baseball team back then had played in Major League Baseball. And in the 1930s, he pitched against Babe Ruth. And so, you know, to me as a baseball fan, that's awesome to think about. You're playing golf with somebody who was coached by somebody who pitched against Babe Ruth. That's not that many connections to go back to get to Babe Ruth. And so this is very similar to the Odish number. These answers are often quite surprising as to how far back you have to go for these things to really kick in. All right, so let's see, what else? All right, so this is some advice from my brother. The first is party less than the person next to you. So I guess you should not have sat in the first row. You're going to have a tough semester. The other one is take advantage of office hours and mentoring. When you get older, people are less likely to want to drag you into their office. I am proud of the fact that I've actually sent public safety after students to make sure they have completed requirements to graduate. Williams will go to this great length. When you get into the real world, this will not happen. Take advantage, not just in my class, but in your other classes. And then the last is learn to manage your time. No one else wants to do this. I have more than enough stuff going on. I don't want to be sending you little emails checking up to follow up. When you have something to do, get it done, get it quickly, get it back to me. The faster you get things back, the more you impress people and the more responsibilities you get. I have gotten a lot of opportunities in life because I do things quickly. And I do things somewhat well for the time it takes me to do them, and that has definitely helped. Other items, I am happy to do practice interviews or to adjust deadlines as you have different things going on in your life. And if you have visiting graduate schools, if you have a job interview, by all means, that is more important than handing in a homework assignment or doing something like this. I will work with you. If you have a big sporting event, by all means, these things are quite easy to work around. Just let me know. All right, last is some useful links. You should know how to use LaTeX and Mathematica. If you don't, you have something to do this weekend. Okay, so here is a link to a web page of mine where I have some handouts on how to use this stuff. They also have videos. They have templates, tutorials, so you can listen to all this stuff and just practice. All right, I think that is basically it, other than the GRE, one of the worst triples of letters for those of you who are going off to graduate school. This is essentially a triage to help graduate schools winnow down large numbers of applicants. You can either pronounce it insurance or extortion. You often have to sign up for 2 GREs your senior year, because if you don't do well on the first one, you need to be able to have the chance to take a second one. These are the topics of what they're on. These are links to a practice GRE exam booklet. I am happy to do some GRE prep in this class. If you're interested in that, email me, let me know so we can work that into the class. Other than that, I think this has now been about 50 minutes of babbling. So your homework assignment, I left it in my office. I had printed out the Benford stuff that I want you to read. I will put it in my mailbox before I leave today at 3 o'clock. I will bring it down to the math colloquium talk at 1 p.m. today, which is Professor Silva, who will be giving the first faculty seminar of the year. I will also just email it to everybody, but if you want a hard copy, I will be bringing it then. All right, it's been a pleasure starting the class. I'm looking forward to a fun semester, and now unfortunately you have to go back to being undergraduates.